Hi, in this video, we're going to be going over 4 practice problems from the USAAAO, that's the United States USA Astronomy and Astrophysics organization, and they host an Olympiad every year where they give tests. So we're going to take 4 of those questions from 2020 and 2021 that are related to our last 3 videos, specifically stellar luminosity and the magnitude system. So let's start with the first question and let's see if we can do it. So this is from the 2021 exam, problem number 2. It's saying, what is the spectral type of a star with a luminosity of 5.86 times 10 to the power 26 watts and a radius of 8.51 times 10 to the power 8 meters? So we see it says spectral type, and if we're not sure what that means, let's take a look at this chart. One way stars can be categorized is by their temperature. Here you can see the temperature ranges, where red stars are actually the coldest and blue stars are the hottest. And with those temperatures, we give them letters, we assign letters to them to identify them. Now you might be asking, why is it O, B, A, F, G, K, M, and not just A, B, C, D, E, F, G? And the reason for this is that originally stars were classified by how strong their, I think, Balmer absorption lines were. And that was in order from A through O, but afterwards we decided to organize them by temperature, and then it got rearranged. So this is the order of the stars with their corresponding temperature, and that's what we have to use to solve this problem. So we can see here that we're given the luminosity already and the radius. So we probably have to find the temperature based on those 2 numbers to find the actual letter that the star corresponds to. So let's start by writing the luminosity formula that we already know. So L luminosity equals 4 pi radius of the star square times temperature to the 4th power times the Stefan-Boltzmann constant. And as a reminder, this is the Stefan-Boltzmann constant over here. And on these Olympiads, you'll usually get a constant sheet that has a bunch of numbers that you don't have to memorize, like the radius of the sun, mass of the sun, some other just constants. Let's start plugging in our values and isolate for the temperature. So I'm going to rearrange this first. So we know our temperature is going to be luminosity divided by 4 pi radius square Stefan-Boltzmann constant to the 1/4 power, because I'm going to undo that. Now, plugging in our numbers. Now I'm going to put this into my calculator, and we're going to get the temperature as 5,808 Kelvin. So now we're going to match this. It seems to match with G, right? Because that's between the 5,000 to 6,000 range. So we can say that this star is a G-type star. And that's our answer. We can move on. Our next question is problem 22 from the 2021 exam, and it's saying, consider an eclipsing binary star system. Let me just go over what that is real quick. So a binary star is like if you have 2 stars, so you have one here and another one here, and the stars revolve around each other. So it's going to go like this and then go behind and go forward, but not just like a planet. The 2 stars go around each other, so both of them move, and they move around one point, which is their center of mass. So the big one would also be moving and cover it up, and then eventually this one would come in front, and what happens is, as they cover each other, their brightness, their combined brightness increases and decreases, because at one point you're not going to see one of the stars. So let's keep reading the problem. Consider an eclipsing binary star system observed in some fixed band to have a combined apparent magnitude of 5.6. So together they have 5.67. During the secondary transit, the second star is totally eclipsed. So something like that. It's totally eclipsed by the first star, and the apparent magnitude dims to 6.25. What percent of the combined flux is produced by the second star? So let's start by writing what we have. We have M total is 5.67, and M 2, which is, let's say, when 1 is covered up, is going to be 6.28. And one thing to keep in mind here is that 5.67 is greater than 6.28. And you might think I'm crazy for saying this, but let me explain. If you remember from our video where we ranked the magnitudes, the sun was negative 26.7. And that negative number corresponds to how bright the sun is during the day. But another star in the sky could be something like a magnitude of positive 1, 2, 3, something like that. So the scale is actually backwards. The smaller a star is, the brighter it is. The smaller the value of the magnitude is, the brighter the star is. And the higher the value is, the dimmer the star is. So 6.28 would look dimmer than 5.67. That's why I'm saying 5.67 as a magnitude is greater than 6.28. But let's go back to the problem. So we need to see percent of combined flux produced by the second star. So the flux, eventually we want the ratio of brightnesses, like B2 to B total, which is brightness of the second star to the total brightness. This is what our answer should eventually be. So to get there, let's use the magnitude formula. So we have M2 minus MT equals negative 2.5 log of brightness of the second star over total brightness. So that's the formula that we were talking about in one of our previous videos. So we can just start plugging in numbers now. 6.28 minus 5.67 right here and here equals negative 2.5. I'm just going to skip a step. I'm going to bring this down here, negative 2.5. Then we have log of B2 over B total. So now we have to undo the logarithm. So we have B2 over BT equals 10 to the power 6.28 minus 5.67 divided by negative 2.5. And from our calculator, we get this is 0.5702. So that's the ratio of the brightness of the second star to the total brightness. And that's 57%. Just multiply this with 100, right? And that's our answer. Now let's move on to some 2020 problems. This is problem number one from the 2020 exam. It's saying the spectrum of a black body peaks at a wavelength inversely proportional to its temperature. This is known as Wayne's law, and we know that. We know the temperature times the wavelength equals 0.002898. So that's the Wayne's law. It's used to estimate stellar temperatures. The sun can be approximated as a black body, which is also a term we discussed in the first video, with its peak wavelength in the visible portion of the spectrum and the surface temperature of 6,000 Kelvin. Given this data, estimate the peak wavelength of a human being, assuming it to be a black body. So since we're trying to find wavelength, we need the temperature of a human body, which is around 98 degrees Fahrenheit or 37 degrees Celsius. And Celsius, now we need to convert to Kelvin because we do all our stuff in Kelvin. So 0 degrees Celsius is 273 degrees Kelvin. So if we're doing this in Kelvin, we're going to do 37 plus 273 is going to get us 310 degrees Kelvin. So now we can plug this into our formula right here. This is simple. So 310 times the wavelength equals 0.002898. Isolating for the wavelength, we have 0.002898 divided by 310 on the calculator, and we get 9.348 times 10 to the power negative 6. 10 to the power negative 6 is micrometers. So that's the symbol for micrometers. That's our answer. So that's a pretty simple problem. Let's keep going. This is question 13 from 2020. The angular diameter of star A with apparent bolometric magnitude of 2 is 2.5 times greater than the angular diameter of star B with apparent bolometric magnitude of 7. What is the ratio of the temperature of star A to that of star B? So there's a word here, bolometric, that you might be unfamiliar with, but let's just skip that and move on. Let's see if we can still do the problem, because a lot of the times in these astronomy Olympiads, they put random jargon that kind of confuses you. But sometimes if you can just ignore it and focus on what you actually know, we know apparent magnitude, we know that system. Angular diameter, that's intuitive. It's just the diameter of a star. If we just stick to what we already know, a lot of the times you can complete the problem and it's not as scary as it looks. So a lot of the times what helps me with these problems is to make a T-chart to see what I already know and what I need to figure out. So I know the magnitude of star A is 2. That M just means it's a magnitude of 2. And then the magnitude of star B is 7. It tells me that the diameter of star A is 2.5 times greater than the angular diameter of star B. That just means that the radius is also 2.5 times greater than star B, so we can do that. And lastly, we need to figure out the ratio of temperatures. So that's what we don't know. I'll just leave those as unknowns right here. So one assumption that we have to make to use the formula that we used here, this one, is that the stars are at the same distance away from us. It doesn't explicitly say that, but if you remember, the difference between absolute magnitude and apparent magnitude is that apparent magnitude depends on brightness. There's the brightness in the formula, where absolute magnitude, there's luminosity in the formula, and the difference between brightness and luminosity again is that luminosity doesn't depend on the distance the star is away from us, where brightness we divide by 4 pi distance away from us squared. But if we assume that the two stars are at the same distance, we can just ignore that denominator of 4 pi d squared for now. So let's just use luminosity. So we have MA minus MB equals negative 2.5. And I'm going to substitute in the brightness formula already. And the brightness formula is the same as the luminosity for the top, 4 pi r square, Stefan-Boltzmann constant, temperature to the 4th power, divided by 4 pi d squared. But if the distances are the same, we just cancel out the bottom for whatever brightness we have on the top and the bottom. So I'm just going to write 4 pi r a squared for the star A, constant, and temperature of star A. Same thing here. Okay, cancel some things out. There. And instead of writing RA square and RB square, I'm going to have 2.5 R square and R square, because that's what we have here. They told us that. And from here, again, we can cancel out the R square and R square. So we're left with 2.5 on the top, the constants, which also cancel actually, and the temperatures. So cleaning this up, because it looks horrible right now, 2.5 log 2.5 times temperature, basically the ratio of the temperatures to the 4th power. Now let's isolate for the ratio of the temperatures. I'm going to plug in MA and MB. 2 minus 7 divided by negative 2.5 equals log 2.5 dA over TB to the 4th power. And eventually, isolating TA over TB, we get an answer of 2, and that's our answer here, C. So the ratio of the two temperatures of star A to star B is just 2. So there we go. We did 2 problems from 2021 and 2 problems for 2020. And I'll see you in the next video. Instead of doing problems, we're going to do more concepts next time. Thank you. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.